Hello everyone. Today we're conducting a quick scientific investigation using a spherorobot to model how forces act on objects moving on inclined planes. Think of it as giving your spherorobot its own mini skate park. Our research question is, how does ramp angle influence the speed of a spherorobot when moving both upwards and downwards? In scientific terms, the independent variable we have is the ramp angle, which we'll be using flat ground, which is 0 degrees, 10 degrees, 20 degrees, and 30 degrees respectively. The dependent variable we have is the robot's speed, which is calculated using the formula speed equal distance divided by time. And the control variable we have include the distance traveled by the robot, the ramp surface, the same sphere device, your own robot, and a consistent timing method. And our hypothesis is that for downward trials, as ramp angle increases, the component of gravitational force acting along the slope will increase, so the spherorobot will accelerate more and achieve a higher speed. On the other hand, for upward trials, as ramp angle increases, the opposing gravitational component will become larger, so the spheromotors will struggle more, like someone trying to ride a bike uphill with the brakes on. The equipment you will need for this quick investigation include your own spherorobot, a mobile phone to connect to and to control your spherorobot, and a stopwatch to keep track of time. You will also need a protractor ruler or some way to measure angles of your ramp. Next, you will also need a way to record your results. For this, I have provided you with this result table along with your task instruction. Finally, for the ramp constructions, since I'm a bit limited in resource, I have chosen to use hard paper and hard plastics from a folder that I find lying around. As for the ramp support, I have chosen to use whatever books I can find lying around, so this task should be suitable for everyone who is limited in resource as well. After a bit of time, here is our finished makeshift ramp, which is constructed by notebooks supported by books to adjust angles. Also, we have a stopwatch for keeping track of time, accompanied by bright colored masking tape to indicate the beginning and the end of the track, which is about 0.15 meters long. And we have a worksheet for collecting results, or rather data collection. Wow, this is very high-tech stuff. Books and tapes. NASA would be proud. And our collection, we will test 4 conditions: flat ground, 10 degree angle, 20 degree angle, and 30 degree angle. For each angle, 3 sets of trials will be conducted and the average will be calculated. The robot will move downwards under the influence of gravity and upwards using a constant motor settings. Here's our ramp of roughly 10 degrees. Here's our sphero control showing it will be traveling for 2 seconds at 100 speed settings. "10-degree angle downward." At 10 degree, the difference is small but noticeable. Downward trials are slightly faster than flat, while upward trials are already a bit slower. 10-degree angle upwards. "20 and 30 degree downward." The sphere clearly speeds up, like a skateboard flying down a steep ramp. However, for the upward trials at these angles, the Zephyr Mini simply did not have enough power to climb, so we had to record NA for those results. This in itself was a learning point. Equipment has limitations just like people do. Across all conditions, we recorded times, repeated trials for accuracy, and then calculated averages. We now look at the completed data table. Here are the average results. We also included flat ground as a baseline. With no slope, the sphere simply rolled at its normal motor speed without any gravitational help. This gave us a point of comparison for the angled runs. As predicted, downward runs became faster as the ramp angle increased. Upward runs became slower at 10 degrees and then impossible at 20 and 30 due to motor limits. The data shows a clear pattern. The downward runs gets faster as the slope gets steeper, while the upward runs became slower early and then stops. This highlights how gravity and equipment power interact. Gravity boosts motion in one way, resists the other, and sometimes wins completely. Students can see that even when results are incomplete, important patterns emerge. They learn how to interpret data honestly, acknowledge obstacles, and adapt when things don't go to plan. In science, that's just as important as a perfect dataset. To conclude, ramp angle has a significant but opposite effect on speed depending on direction. Downward motion is faster with steeper slopes, while upward motion slows and eventually becomes impossible. This mirrors everyday life, like cyclists racing downhill but struggling uphill, or me sprinting towards the canteen at lunch but dragging myself back up the stairs afterwards.